Hello everyone and welcome to another video. Today I want to talk about how to convert a constrained optimization problem to an unconstrained optimization problem using the penalty method. So this video is part of our series discussing optimization algorithms, so I'm going to assume that you're somewhat familiar with the basic concepts of optimization. If not, please feel free to check out some of our previous videos. I'll try to leave links to those in the description below. So that being said, let's just jump right into it. So I just wanted to quickly flash up a couple of the different types of problems you might see in optimization. So the first one, which I'm calling the unconstrained, which is the UC subscript here, is basically just minimize some function here, right? And it's unconstrained because there are no constraints associated with it. All you need to do is pick a value of x, which minimizes this function f0. Of course, this function f0 could be nonlinear, it could be complicated, etc., etc. But the nice thing about these unconstrained optimization problems are they are very readily accessible to a wide variety of optimization algorithms, such as MATLAB's fmin search or other types of algorithms. So these are nice. Maybe while we're staring at this, before we jump it too far into it, maybe I will mention I'm going to use the notation x here as our decision vector. So note, I'm not going to explicitly draw a bar over this, but again, I'm going to assume that you're familiar with optimization and you understand that this function f0 is a function of potentially many variables all stacked up into this one vector x, okay? All right, so this is almost like the simplest situation. We would love it if you could get situations to be an unconstrained optimization problem, because a lot of times these things are simpler. However, that's not always the case. Usually the more general situation would be a constrained optimization problem, which I've denoted right here, kind of after this red line. So P constrained is, again, the same idea where you want to minimize some kind of cost function here. Again, I'm going to call it F0. However, you are subjected to various different types of constraints. You could have inequality constraints, which are written right here. So this is f1, 2, 3, all the way up to fn. All these functions need to be less than or equal to 0, right? So these are n number of inequality constraints. So this helps shape the feasible set of your problem. You could also have equality constraints here, right? You could have up to m equality constraints as well, which again also kind of reduce the dimensionality of the problem and also shape the feasible set, however you'd like to think about equality constraints, right? So this is the more general case, but obviously it's the more complicated case, right? Because not only do you have to minimize some function, but you have to respect the feasible set of potential solutions by satisfying the inequality and the equality constraints at the same time. So the discussion today is, how could we potentially take a constrained problem and reformat it or repose it as a unconstrained problem, okay? So that's the vision of where we would like to go. So that being said, to first get a better handle on how we're going to go about this and what this penalty method is all about is, let's consider this third type of problem down here. So again, I've tried to outline and delineate with this red line the three different problems that we're looking at right now. The third type of optimization problem that I want to consider right now, just to understand the behavior of where we're going to go and how we're going to approach this, is let's look at this third problem. I'm calling it equality constraints only, or EO. So again, it's minimize the cost function, but I only want to consider equality constraints right now. Let's ignore these inequality constraints. We'll come back to them later. But for now, let's look at a problem that fits this box right here, an equality constraint only problem. So you know me, I like to look at concrete examples. So let's look at an example here of a 2D quadratic. Okay, so let's go ahead and define a cost function. Let me switch pens. That one is kind of on its way out. So let's go define our cost function. How about like this? So f0 of x is going to be 1/2 x transpose times h times x plus g transpose x plus r, where these matrices slash vectors. So first let's look at h. H is going to be a 2x2 of 1, 1, 1, 2, and then g is going to be a 2x1 of 1, 2, and finally r is just a scalar constant of 2. Okay, so I want to solve this. Here is my cost function, and let's look at the first equality constraint here. So the equality constraint of f1 of x is going to be x2 minus x1 plus 8 has got to equal 0, okay? So in this case, the example problem that I'm looking for is, again, minimize this cost function subject to this constraint right here. right? So the first thing we should do is, again, maybe we should jump over to MATLAB and just visualize the problem and think about what this means, okay? So again, the space of all of our solutions here are x1, x2, right? And this cost function f0 is defined over it. So we're going to see when we jump over to MATLAB, this is a quadratic. You can kind of see just from its shape. So there's this bowl shape defined over this. But here we see that x1 and x2 can't be anything. We're not allowed to pick anything in this space. So in fact, maybe what might be easier is if we solve for a relationship of how do x1 and x2 have to relate to one another. I mean, it's pretty easy. If you solve this thing for x2, you can basically say that x2 has got to equal what? x1 minus 8, right? So x2 is, it's got an intercept here of minus 8, right? And then a positive slope. So something like this, right? So it's got to lie along this line, right? So tell you what, let's run over to MATLAB, visualize this picture. We'll visualize the constraint and the objective function and get a better understanding of what we're really asking for in this equality constraint only problem.
All right, so here we are, and I've plotted in MATLAB the cost function, which is that quadratic you can kind of see here in all of these blue and yellow shades. And then I've plotted in the red dashed the constraint F1. So you can see that what the problem is now, the equality constraint only problem is basically saying try to find the minimum function value along this red line. So you can kind of see that it's probably, somewhere in this neighborhood. Something like this. And in fact, tell you what, to give you a better view of this, let me tilt the picture just so we can see what it looks like. So let me change the viewpoint, and you can see again the cost function is this bowl-shaped object, right? The constraint is down here in the x1, x2 plane, right? So that's this red dashed line here, and what I've done is I've projected that line up onto the cost function surface just to give you an idea of what's going on. And I think if you do that, you can kind of see that what this equality constraint does here is it actually kind of lowers the dimensionality of the problem. So instead of having to search for a minimum over this two-dimensional surface, right, which is this entire shape that we plotted here, I only have to search for a minimum along this red dashed line, right, which is really a one-dimensional object. So tell you what, let's jump over to actually, how about to like Mathematica and analytically solve for where is that minimum. Again, we see that it should be, somewhere around here, which then, is somewhere down here in the x1, x2 plane. So let's switch over to Mathematica and find that analytical solution right now. All right, so here in Mathematica, let's go ahead and just enter in our definition of the cost function here, and what we should see is that it's just a quadratic as we expected. Now, what we saw is that if we were to enforce the constraint 1, that means that x1 and x2 are related, right? In other words, x2 has to be x1 minus 8. Right? That was the relationship. So really what we can do is then we can evaluate this cost function here along this relationship. In other words, I can look at f0 when x1 is free, but x2 is not free, right? x2 has got to be x1 minus 8, right? And what we should get here is maybe let's say / simplify. Let's blow this up a little bit. Again, we get a scalar. We get a function of just x1. Maybe let's call this f0 scalar, right, as only a function of x1, okay? And let's go ahead and plot this thing just so that we can see what it looks like. And I've got actually that prepared off screen so you don't have to watch me fat finger type in that input. And here's what it looks like. So again, this is effectively that red dashed line that we looked at in MATLAB. This is what it looks like, right? It's only a function of x1. So you can clearly see the minimum is right here. And in fact, it's pretty trivial now to find the minimum of a scalar quadratic, right? All we have to do is, well, what do we have to do? We have to take the derivative of the scalar, right, of that function with respect to itself, right? This is the derivative, and we basically have to solve where is the derivative equal to 0, right? Solve this equal to 0, solve it for x1. So there, that's the solution for x1. So this is apparently the x1, let's call it x1 star, right? That is our optimal solution, right? And what is that in as a number, actually? Let's ask. Whoops, so x1 star. Yeah, it's at 4.2, which, yeah, it looks exactly like that here on the plot, which makes sense. So that's the optimal solution of x1, and therefore x2 star, right? We said x2 is related through this, right? So x2 star, the optimal x2 has got to be x1 star minus 8, right? So it's negative 19/5, and again, I guess let's look for that as a number. So minus 3.8. So we've got the optimal solution. So the optimal solution to the equality constraint only problem is what? It's x star is got to be, in this case, what, 4.2 and negative 3.8. Okay, so let's keep that in mind, and let's jump back to the board now and talk about this a little bit.
All right, so coming back to our picture, I think we said that the optimal solution was here at an x1 of 4.2 and an x2 of minus 3.8, right? That was the correct answer. So maybe let me just draw it here on the line. It says red x, right? So this is the optimal solution. Okay, and again, I think we denoted that as x star, right? That was our optimal solution. So now, you know what we should do is let's step back and think about this. What does this actually mean, right? So again, let me rewrite the equality constraint only problem, right? We said we were trying to minimize f0 of x, right? Which was this quadratic here, such that f1 of x is equal to 0, right? So this was the equation of that line, right? Of this line right here. So what we're really sort of telling the optimizer, right, if you think about this long enough, is you can do whatever you want as long as you stay on this line, right? The constraint here, right? That's the idea with the constraint is it's something that has to happen, right? You have to satisfy this constraint in order for the solution to be feasible, to be a valid solution, right? It's like telling the optimizer, yeah, like I said, do whatever you want, but if you step off this line, you die, right? You get no more chances, you get no more extra guys. You cannot step off this line. It's like you're up on a high wire 1,000,000 feet in the air, and if you fall off this line and choose a solution that's not on the line, you die, right? Well, could we get the same or a similar result if maybe instead of saying if you step off the line you die, what if we said something like, if you step off the line, maybe we're gonna penalize you for doing that? And maybe we will penalize you so much that it's almost like dying, right? So we could say like, okay, if you step off of this line, we are going to chop off both of your legs and your arms and punch you 6 times in the gut, right? You might not die, right? But it's pretty undesirable, right? So hopefully maybe if we could shuffle it, do something like that, reformulate it, the optimizer might think, you know what, that's almost like death, but I guess it's not exactly like death, so maybe it's still okay, right? What I mean by that is, could we take maybe this constraint, right? This was a hard constraint, and potentially, what if we think about moving that into the cost function so we penalize the system when it's not enforced? So what I mean is maybe we should just write this down mathematically. What if we could reformulate this as another problem? Let's call it maybe P approximate. P approx, right? So now I'm going to minimize f0 of x, the same thing, but now I'm actually going to add on to this cost function. So let's make a new cost function. Let's maybe f0 hat, which is going to be the original f0, right? The original cost function, but then let's add on plus, how about alpha f1 of x squared? Okay, so you can see what we've done here is we've taken this hard constraint and we've moved it into the cost function, okay? So here, this alpha is going to be greater than or equal to 0, and this is sometimes referred to as a penalty parameter. Okay, and then this term here, the f1 of x, notice it's squared. That squared is very important here. So this term, f1 squared, is the penalty function, right? It is not the same thing as the constraint function f1. It's actually the constraint function squared, okay? So let's look at this approximate problem here and ask ourselves, is it similar enough to the original equality constraint only problem? So let's make a couple of observations, or let's make a couple of notes. So note a few things about this. One, the first thing to note here is, if you look at this, P approx has no constraints. right? I don't see any hard constraints where I say something has absolutely got to be enforced, right? So therefore, right, we can say P approx, right, is an unconstrained problem. S-T-R-A-I-N, constrained problem, right? Okay, so that's handy. Okay, the other thing that maybe we should note here is, let's see, and we'll note here that the term f1 of x squared, right? This penalty function that we had here, what's nice about this, if you look at this thing is greater than 0, right? Whenever f1 of x is not 0, right? So when f1 of x is not equal to 0, right? This penalty term is increasing, okay? So if you think about this, right, and if you look at it, you can also say that maybe a related thing to note here is this term f1 of x squared, right? This thing actually equals 0, right? Where does it equal 0? The only way you get this term to equal to 0 is basically if and only if f1 of x is equal to 0, right? So if you think about this, what does this bottom line mean here, right? This happens if and only if, right, f1 of x is satisfied, right? In other words, if constraint, maybe we should reword this. Maybe we should say if and only if, let's call this constraint 1, how about? Right? So this is fascinating. This penalty term here, it's 0. The only time it's 0 is if you've actually satisfied constraint 1. Otherwise, the cost just goes up, right? It's positive everywhere else, which is why this squared term is so important here, right? It's going to make it so that this penalty function, the only way you minimize the penalty function is if you satisfy constraint 1. Otherwise, it's just going to, its cost is going to increase, right? So the last thing that maybe we should notice is here. Let's make another note here. So 3 here. This composite cost function here, f0 hat. So let me write this down. f0 hat of x, right, is minimal when Right. It's minimal when the composite of these two terms here, right? This is minimal when f0 of x plus alpha f1 of x squared is minimal. And what's important about this right now is this may not necessarily be when f0 of x is minimal, right? And the reason we call that out here is because if you remember, this f0, this was the original cost function. Cost function, right? Okay, so really we are trying to minimize, I mean here you can see this is the original problem, right? The original equality problem said minimize f0 such that the constraint is satisfied. What we're doing here in this approximate problem is something slightly different here. And depending on this value of alpha, it's going to depend, and we're going to see that has some influence on how well we are, how close we are to solving the original problem by solving this approximate problem here. Okay, so this alpha term then is effectively our tuning knob that we can use to try to tune how the solution of this approximate problem, right, will hopefully converge toward the solution of the original problem, right? That's our game plan. So maybe what we should do here is, let me go ahead, give me a moment to pause the camera and erase the board, and let's continue on with modifying our quadratic example to be our approximate problem. All right, so I've erased some of this to get us some room. So let's just go ahead and make f0 hat, right, our approximate cost function. So that's pretty easy, right? We said f0 hat of x is just going to be the original cost function. So in our case, it's the 1/2 x transpose hx plus g transpose x plus r, and now we're going to add on the penalty term, right? So the penalty parameter alpha times f1. f1 was this, right? Here's our constraint. So this is x2 minus x1 plus 8. And again, do not forget this squared term. That will mess you up if you do. So here we go. And if you look at this long enough, we'll do this in Mathematica in just a second, but take my word for it that this thing, if you notice, it's just going to end up being another quadratic in x1 and x2. And again, you're going to have this parameter alpha floating around in here. So long story short, this whole thing is just a quadratic in x1, x2. Right? With alpha hanging around. So the more important thing to also think about is since it's a quadratic, and if you look at this, right, this is an unconstrained problem. So I can actually analytically find the solution or find the minimum of this unconstrained, of this function here, right, with no constraints, by basically finding, I just need to take the gradient, find the gradient, the df0, or f hat, right, dx, right, which is just going to be a gradient. It's going to be partial of f0 of, again, I keep forgetting that hat, right, with respect to x1, and then partial of f0 of x with respect to x2. Again, there's the hat, right? I got to find this. When does this equal 0, 0? Right? Find the x1 and x2 values that make that happen. So, tell you what, let's jump over to Mathematica and actually have it do that. And again, the thing to remember is that it's going to end up being a function of alpha. Right? Alpha is going to bake its way into here, so obviously the solution is going to be a function of alpha. So let's go over to Mathematica and do that now.
All right, so why don't we just pick up where we left off, and what we want to do now is define f0 hat of x, right? So what do we say? I think we first need to define f1. I don't think we defined that earlier. So here's our constraint f1. So now the overall f0 hat was just going to be, let me go ahead, I've actually got this prepared off screen so you don't have to watch me input it, right? It's just going to be the original cost function plus here's our alpha and then our f1 squared, right? So again, if you expand this and look at it, yeah, look at it. It's just a quadratic in x1 and x2. So now let's go ahead and compute the gradient. Right? So this is, I need to take the derivative of f0 hat with respect to x1. Right? This is going to be let's call it df0 hat dx1, right? Okay, there's the first one, and then I need to also take the derivative with respect to x2. Oh, wait, whoops, sorry, I messed this up. It should be x1 and x2. Sorry, there we go. Okay, there we go. That's a better term for the expressions. Okay, there we go. That is our two expressions for the gradient, and now what we need to do is just find where the gradient is 0. So I need to simultaneously solve for when this guy equals 0, and I'm going to solve for when this guy equals 0, right? That's my system of equations. Let me put this in braces so we get our system of equations there. And I want to solve this for x1 and x2, right? Those are the two variables I want to solve for. And here we go. Here's the two solutions that we end up with. So apparently x1, maybe we should call this x1 hat star, right? Is this first value, right? That was the first solution, and x2 hat star is this guy. Okay? So again, as we said, this is a function of basically of alpha. And if you think about this long enough, right? If alpha is 0, the problem reverts to basically a completely unconstrained problem. It means like we don't actually take into account the constraint. So if we start cranking up alpha, though, what we're doing is we're effectively starting to, let me come back to our definition right here, right? We start to make the penalty for stepping off of the line or for not obeying the constraint, we start making that more and more and more, right? So why don't we go ahead and, just for giggles, take a look at what does x hat star, x hat 1 and x hat 2 star, what does this look like if alpha was, say, 1? Right? Okay, so if we do that, and actually, again, I don't think the fractions are helpful. Let's look at this as a number. Whoops. Let's do that. Okay. So here we go. Look at this. You get a value which is, 3.8 and minus 3.5, which is actually, not too far from the actual solution, right? We know the real answer. If we scroll back up, right, this is what we came up with earlier, right? When we properly solved the equality constraint only problem, this is the answer we got. This is what we should get: 4.2 to 3 and 3.8. Well, look at this. As you start increasing alpha, though, let's make alpha a little bit higher. Let's make it 2. So now we're saying the penalty for not obeying that constraint is even greater. And look at this. We're getting closer now, right? We're getting closer. If we keep cranking this number up, like let's make alpha up to 5 for... And look at this. This is effectively, I mean, we're basically there, right? We said that the true optimal, let me just copy paste it so we can stare at it at both of it at the same time. Look at this. We're getting really darn close, right? 4.177 instead of 4.2, and then here we go, this instead of this. And I bet if we keep cranking this up, here, let's for giggles, let's go by an order of magnitude. Let's make it 50. Look at that. We've basically solved it. So this is really powerful in the sense that, think about this. We basically have now used an unconstrained approximate problem and solved it, albeit we solved it analytically, and we are getting the correct answer, right? We are getting the solution to the constrained problem this way. Now, like we said, this analysis that we just did here, if you think about this, we had to go through and we had to analytically solve this, right? This is what we were doing by solving the gradient, right? We were assuming that the problem was simple enough that we could actually, that this line right here was feasible to do in Mathematica. This is not always the case, right? If your cost function was complicated, you might not be able to analytically solve this, and you might need to use a numerical method, like, say, MATLAB's fmin search. Well, we can still use this penalty method where we would go ahead and compute this augmented or different cost function and then throw it in a numerical algorithm like fmin search or something like that. So, you know what? Let's look at that right now. Let's pretend, say we didn't know how to do the analytical solution of this approximate problem. Could we go ahead and use MATLAB and a numerical technique to actually get me that solution? So let's jump over to MATLAB real fast. All right, so here we are in MATLAB, and I've actually just put a breakpoint and run to this point in my code. Don't worry about these previous 60 lines of code. All that was doing is actually generating this plot that I was showing you earlier, which was basically the cost function, the constraint F1, and now what we've done here is I plotted this green X, which was the constrained optimal solution. I think this was the X1 of 4.2 and Y of minus 3.8, right? So this is the solution we want the approximate problem to solve and get to, okay? So I'll tell you what, you know what we should do? Let me just dock this here so we can look at everything all in one time. So what we're doing now here in this bottom loop here is I'm actually defining a whole bunch of different alpha values that I want to experiment with. So you see I'm starting here with first with kind of a small range. I'm going from 0 in increments of 0.1 up to 0.5, and then I'm jumping to 1, 3, 5. So basically, long story short, this thing is a slightly non-linear range of alpha values that I want to try this solution problem with, right? I want to try to solve the approximate unconstrained problem with different values of alpha. So that's all I'm doing in this loop here. As you see, is we're dropping down, and maybe we'll advance in the first loop. So I'm going to pick up the first value of alpha. So the first value of alpha is 0, right? So this should be a completely unconstrained problem right now. So here on line 69 and 70, I'm defining an anonymous function handle, which is basically the augmented cost function that we talked about earlier, but I'm going to allow myself to change the value of alpha. So maybe let's look at this function real quick, just so you can see that it's nothing fancy. It's exactly like we talked about. I'm defining the H, G, and R. So here's the original cost function, right? Here's my original quadratic cost function that I wanted. Here's the original constraint, F1. And now I'm making the augmented, unconstrained, approximate cost function, which is the original cost function plus the penalty parameter times the penalty function here. Right? So that's all this function is doing, and the reason back here in the main script why I've got this as an anonymous function handle is so that I can call fmin search and pass in extra parameters. So if this is confusing to you what I'm doing right here, it's really not that bad. In fact, I made a completely other video describing how to use fmin search and how to use and call it with different techniques. So please, I encourage you to watch that video if you're uncomfortable with what's going on here. Again, it's nothing really fancy. All this is allowing me to do is it's allowing me to call fmin search and call this function here and change the value of alpha as I want to do every time through this loop just to do some experiments. So let's keep stepping through this. And here on line 73, I'm just defining an initial guess. I might as well start at 0, 0 since I don't have a great idea. I'm going to pretend I don't know where the solution is. And now here on line 74 and 75, I'm basically calling fmin search to try to find the solution numerically. And again, keep in mind now that since alpha is 0, what it's doing is it should be solving the unconstrained problem. So it should be completely ignoring this red line, right? We're basically telling the system there is no penalty for stepping off this line. You can do whatever you want. Feel free to just ignore this line. You don't have to stay on it at all. So we expect the solution to be right here, smack dab in the middle of this quadratic, right? So if I run this line, let me run that. Here we go. Now on line 78, I'm plotting that value that it just kicked out as a magenta plus. So let me plot that here, and I guess we can't see it because it's underneath. Let me go ahead and actually, I guess that's what I'm going to do on line 80 is I'm going to change the viewpoint of this because the solution is sitting underneath this surface. So if I do that, yes, there you go. You see, this point is the one it just found, and if you project it straight up, you will basically end up at the very bottom of this surface, right? It completely ignored the red line, right? It completely ignored the constraint. Now, let's run through this loop again, okay? So I'm going to come up here. I'm going to pick up a new value of alpha. So now alpha is 0.1. So again, we go through the whole exercise again, and now on line 74 and 75, when we run fmin search again, we're again telling it to minimize the cost function, but now pay a tiny little bit of attention to the red line, right? This magenta circle or plus sign, you can't stay here any longer. You have to pay a little bit of attention and try to make an effort to also solve and satisfy so that you're on this red line, okay? So that's all I'm doing here. Again, let's run it again. Let's plot the solution. And hey, look at that. It started moving towards the proper location, right? We expect it to hopefully converge to this green X, right? So again, that's what we do. So tell you what, let me take off these breakpoints. You see I have a pause statement in here, so it's going to go through and going to pause for 1 second. So we should see it draw a new value, pause for a second, draw and solve a new value, etc., etc. So if I let this guy run, we should see what's going to happen. How does this system behave as alpha starts increasing, as we start jacking it up and up and up. And in fact, up here in the top of the plot title, you'll see the current value of alpha. So with all that said, let me just hit run and we'll see what happens. So as you can see, as alpha increases, it starts paying more and more attention to that constraint, and eventually, like we saw here at alpha of 5, we've basically converged to the location that we were expecting. So if we come out here and look at what is x hat star, we see that it is way darn close to the 4.2 and the minus 3.75. So again, the beauty of this approach that we're doing here in MATLAB is, yeah, we got the exact same result that we got in Mathematica, but we got there a completely different way. We did this with a completely numerical technique using fmin search as opposed to having to calculate any gradients and try to do any fancy solving, right? So this is an incredibly powerful technique. And what we should do now at this point is maybe let's jump back to the board and think about how can we expand this maybe to more constraints or even maybe to inequality constraints.
All right, so let's talk about what if we had multiple equality constraints, and actually what if we had more than just 2 dimensions, right? For our original problem here, it was minimize f0 of x, right? And we said x was basically in R2, right? Right, there was 2 variables. and we only had one equality constraint. But you can see the nice thing about this is we saw how to basically make an approximate problem here in this case, but if the dimensionality was higher, right, like if we had p dimensions, right, with p decision variables, nothing would change here. This would still be the same thing. And in fact, if we had more constraints, right, what if we had an f2 of x has got to equal to 0? Well, I think you can see that it's not that hard to do. What we would just need to do is make this now like an alpha 1, and now we would have plus an alpha 2 f2 of x squared. And now the alpha 1 and the alpha 2, these are two separate parameters that we could use to tune how much do we care about satisfying constraint f1 and how much do we care about satisfying constraint f2, right? And you can see this just goes on. You just start tacking on as many constraints that you've got, again making sure to square each one of them. So extensions to higher dimensions and multiple equality constraints really isn't that big of a deal. And now that we've got an idea of how this operates and how we can handle equality constraints, we can basically take that and try to address inequality constraints as well. All right, so let's take a look at how we can extend this idea to inequality constraints. So just to recall, right, for equality constraints, right, the ones we just looked at, we looked at penalty functions, let's call them p of x, right, of the form fi of x squared. Right? Now, they don't have to take this form, right? This is one that we just chose, and it happens to be a fairly popular one for equality constraints, but we make a note here that the key characteristics of p of x, right? There's a couple of things that are important, right, that we leveraged in developing that approximate solution, right? It was a couple of things. One here was, well, p of x is continuous. Right? The second thing that we made use of was that p of x was greater than or equal to 0 for all x in your solution space. I think if we said maybe you have p decision variables, right? And then the last thing that was kind of the key was that the penalty function was basically 0 if and only if fi of x was equal to 0. In other words, this thing was 0 only if you satisfied that equality constraint, right? Okay, so now what about for inequality constraints? So let's maybe draw a line down here. We can kind of compare and contrast. So for inequality constraints, remember, these take the form of fi of x has got to be less than or equal to 0. So it doesn't exactly have to be equal to 0. Negative values are totally fine. In fact, those are encouraged or totally great. Those are perfectly feasible. If you choose an x and this function evaluates to like negative 18 billion, that's not a problem, right? It was a problem over here in your equality constraints, but it's not a problem here. So in this case, what we need to do is we need to choose a slightly different penalty function to take that type of behavior into account, to basically say it's okay to be negative, right? We just can't be positive, right? So in other words, the popular one to choose here is, let's just write it down and then we'll talk it through. It's the max function between 0 and then fi of x, and then the end of the max and then squared, okay? So a couple of things to note about this function. Again, let's write this down and then we'll see how this works. So the first thing to note here, is make sure that you note that the square is outside the max function. So don't make this mistake. This square is not on the fi term, right? It's actually outside this max. So you take the max between this and 0, and then you square it, right? Do not square the inequality function evaluated at the location and then max it with 0, right? You always want to make sure that this square is on the outside. So again, this is a very easy mistake to make, so I want to harp on this and make sure we drive it home. The square is on the outside of the max function, okay? So if we're cool with that, right, the next thing to note here is that, well, if you look at this, let's think about this. fi of x, right? It's basically, this thing is always greater than 0, right? If you look at it long enough, p of x is greater than or equal to 0 for all whoops, for all x, right? For all x in RP, right? Again, you've got P decision variables. So let's think about this, right? We can talk this through. Let's say you choose an x such that this inequality constraint, this function, whatever it happens to be, evaluates to negative 18 million, right? By the time you take a max of negative 18 million and 0, you get 0, right? Now, conversely, let's say that this function evaluates to positive 18 million. You take the max of 0 and positive 18 million, you get positive 18 million. So no matter what you do, this P of x is always greater than 0 for any value of x you choose, okay? Now, the next thing that's very nice about this here is, let's say if fi of x is satisfied, meaning that fi of x, we should write this down, meaning fi of x is less than or equal to 0, right? What this means here is that if you look at it, if it's satisfied, this function is less than 0, but by the time you take the max of it, right, you get 0. So what you're going to end up with here is that basically the max of 0 and fi of x, and this whole thing squared, this thing is going to be 0. Right? Again, this is if it's satisfied, right? So if it's satisfied, then the max of this thing is equal to 0. Therefore, right, the other way you can think about this is that P of x is going to be 0. So the penalty function is 0 when you satisfy the constraint. And again, maybe this is a little confusing nomenclature. Maybe we should call this, like, we should say constraint I is satisfied. So this penalty function evaluates to 0 when constraint I is satisfied, okay? And a corollary to that, or a related one, is this P of x, right? The way this thing is greater than 0, right, is when, how do you get this thing greater to 0? Well, you look at this max function, right? This thing has to be positive, right? Yes, right? So the whole penalty function is 0 when fi of x is positive, right? And what does this mean? This happens when constraint I is not satisfied. So again, this penalty function has really key characteristics very similar to the penalty function we chose for equality constraints, right? Namely, items 3 and 4 are basically what we want to do, because this is awesome. The penalty function, whenever you're not satisfying the inequality constraint, the penalty function is positive, right? You incur some cost. The only time the penalty function is 0 and is not hurting your optimization problem or your cost function is when the constraint is satisfied. So this is pretty darn great. So with that being said, I think what we should do is let's think about looking at an example where we want to now add both equality and inequality constraints and look at appropriate penalty functions and see if we can get a numerical solution in MATLAB. Okay, so tell you what we should do is let's go ahead and maybe we've got enough room here, is let's go ahead and revisit our 2D quadratic, right? The same problem we've been looking at today, right? So revisit 2D quadratic, right? So if you remember, right, the constraint problem here in this case was minimize f0 of x, right? Which was, again, that was our good old friend, the 1/2. Let me see if I can just make sure I don't write it down incorrectly. It was way back here at the top of the notes, right? It's the first thing that we started with. So it's 1/2 x transpose hx plus g transpose x plus r, right? Okay, and then such that f1 of x, right? That was our first constraint. That was the equality constraint that we were dealing with earlier this evening, right? That was x2 minus x1 plus 8. It's got to equal 0, right? So here's f1. Now what we want to add is let's add a second constraint, f2 of x. right? So this is going to be, I'm going to again make something up. How about 2x1 plus x2 plus 4 is less than or equal to 0, okay? So this one that I'm kind of outlining in blue is the new term that we're adding to it, right? Okay? So, okay, that's the new game plan. All we've done now is added this inequality constraint. So we've chopped down the feasible set. We've made it smaller, okay? We've constrained the problem a little more. And now what we want to do is see, can we go ahead and now formulate this as an approximate problem using these penalty functions that we talked about earlier. So let's write this down. Gosh, I'm running out of room. I think we can squeeze it in here. Let's tell you what, let's get rid of items 1 and 2 because we don't really need those. Okay, so the approximate problem, right? We're going to transform. Here's the real problem we're trying to solve. Now our P approximate, right, is we are now going to minimize F0 hat, right? And here, F0 hat of x, right, is going to be the original cost function, F0 of x, right up here, plus, now we already know how to deal with the equality constraint. We just did that. Let's make this an alpha 1, F1, or I guess tell you what, let's just call it penalty function 1. Alpha 1 times penalty function 1 of x, right? And penalty function 1 of x, crud, I'm going to erase all this. We're just going to get some more space so we can write this out in a reasonable fashion. Okay, so here, penalty function 1 of x, right? This was dealing with our equality constraint. So we said that the appropriate form of that was basically f1 of x squared, right? Okay, but now we got to deal with this inequality constraint, right? So now plus alpha 2 and then a second penalty function, like such, right? And now P2, the second penalty function, is this an inequality constraint, so we're going to use this max here, right? So now we're going to use max between 0 and f2 of x, and then square that whole thing, right? Okay, so yeah, that's what we're looking at. Tell you what, let's go over now to Mathematica and first try to suss out and analytically think about what is the answer we should be getting. And once we do that, we will go over to MATLAB and see if we can get that same answer numerically using fmin search to solve this approximate unconstrained problem.
All right, so back here in that same Mathematica notebook, let's go ahead and define the F2 inequality constraint, right? We said, I think that's what we had on the board, so I'll shift enter and get that into Mathematica. And now all I want to do is actually, let's just visualize the feasible set. So I want to plot F1 and F2. So let me just paste this code in from off screen. And again, we don't need to really care too much about it. Let me just go ahead and enter it in and we'll take a look at what it is. So what we're doing here is I'm just drawing the feasible set. So this line right here, this is the constraint F1. If you remember, what that basically said was the solution has to lie on this line, right? Now, this green circle was what the optimal solution to the equality constraint only problem was. This was that value that we had earlier of, I'm trying to remember what exactly was it. Yeah, 4.2 and negative 3.8, right? Now, what we've done just now is we introduced the inequality constraint, which is this entire region over here in blue, right? So anything in this region in blue also has to be satisfied. So we see that what we've done now is you've said that we can only choose solutions which are on this line, basically, which would satisfy the constraint F1. And it has to simultaneously intersect with this entire region here, which satisfies constraint F2. So we see that basically the solution has to lie basically somewhere on this line that I'm trying to highlight right now. And just from how we know what the cost function is doing is just a simple quadratic on this area with a minimal down here. If we were just walking on this line, we see that now the solution to the constrained problem, which has one equality constraint and one inequality constraint, it should be right here at this intersection, right? So now that we've sussed that out and we understand what the feasible set looks like, let's now try to apply this penalty method to the numerical optimization algorithm in MATLAB using fmin search. All right, so here we are, and I've modified the code to reflect our equality and inequality constraints, and it's a very minor change, right? So now we just need two alphas, an alpha 1 for the equality constraint and an alpha 2 for the inequality constraint. Just to keep things easy, I'm using the exact same number. So again, I'm just going to cycle through various ranges of these alphas, starting from 0 and going all the way up to 5. So let's run this. Well, again, before we run this, maybe let me go ahead and grab the figure, and I will dock it so we can, again, watch what's going on. So, again, the red line is the F1 constraint. This new cyan line is the F2 constraint that I've added. Remember that this is an inequality constraint, so anything kind of in this region, sort of to the left of the cyan line, is valid. So again, what we're expecting is the solution to end up somewhere around here. Again, the green X is the solution for the equality constraint only problem, right? So we know that's the wrong answer because now we have to obey two constraints. So we're hoping that the solution, the numerical solution, as we start running fmin search, is going to converge to sort of the intersection of these two. So again, I set this up in exactly the same way with an anonymous function here, and I've just changed the cost function, right? This is the cost function f0 hat, right? It's the augmented approximate problem. So let's again take a look at it just to show you that it's nothing fancy. Again, here's f0. Right? Same thing we saw last time. Here's F1, same thing we saw last time. And now here's F2. Here's the new addition, right? So F2, and because it's an inequality constraint, we see that the penalty function that we're using right here is now this max between the two of them, and then we square it outside the max. Right? So this is my overall new cost function. It's a combination sum of the original cost function, the penalty parameter and penalty function for the equality constraint, and then the penalty parameter and penalty function for the inequality constraint. So if we go ahead and let this thing run, let's go ahead and run one iteration of this. Again, that changes the view here. And again, we see, again, with alpha of 0 for both of those two, we're basically ignoring, again, both constraints of F1 and F2. So again, the solution is not feasible, right? It just picks what is the minimum of the original cost function. But now if I take this off and again let this thing run through the alpha ranges, we should hopefully see the magenta pluses. They should be going not to the green X, right? Again, the green X is if you only cared about one of the constraints, but now we care about two. So really, I'd like to see it coming down here to this intersection. So let's just run this guy. And as you can see, that is indeed what we get. As we start cranking up alpha, we start paying more and more attention to that constraint, to both of the constraints, until we end up with a solution. So right here, this is, if we evaluate this, and I guess we got to come over to the command window, this is our new solution that satisfies, well, or at least gets close to satisfying both the equality constraint and the inequality constraint simultaneously.
All right, so there you have it. To summarize, what we covered today was a technique to basically take a constrained optimization problem, right, and convert that into an approximate equivalent unconstrained problem using what's called the penalty method, right? So if you're looking for more references on this technique, yeah, it's referred to usually as the penalty method. This was first developed by Fiacco and McCormick in 1968, and in fact, an excellent resource and reference for this is the book by Jensen and Bard. It's Operations, Research, Models, and Methods. I'll leave a link to that down in the description in case you're interested. As well, if you're interested, this is also closely related to what's known as barrier methods. So in this case, this was a penalty method where we would penalize you for stepping off or for violating constraints, right? Another way you could do this is by creating barriers around the edge of the feasible set. So as you approach the feasible set in your solutions, this barrier would sort of push the solution back. And again, it's similar. It would be a way of sort of penalizing getting too close to violating those constraints. Now, what I want to do though is use this, and we want to set the stage that although we talked about applying this penalty method in a somewhat academic exercise today using this, fictional quadratic and some of these simple constraints of equality and inequalities, in future videos, in fact, in the immediately following next one, this one right over here, we're going to show how you can use this penalty method to actually solve multiple equations simultaneously. So it's incredibly useful for a lot of practical engineering. And in fact, in another future video, we'll actually even look at how you can use this to do cool things like how you can trim an aircraft model to fly in different flight conditions by applying a variation of this penalty method. So this optimization penalty method, because we approached it from a very mathematical, theoretical framework today, it's going to lay the foundation to allow us to extend it to a lot of these cool engineering topics that we want to look at in the future. So, with that being said, I think this is a great spot to leave it. I hope you enjoyed the video today, and if so, I hope you'll also consider subscribing to the channel. If you just scroll a little ways down and click on that subscribe button, it really does help me. I would also love to hear from you, so if you would like to see other optimization discussions or topics, please leave me a comment below. I read all of those, and it's a real good way for me to get feedback from you guys. So, with that being said, I do hope to catch you at one of these future discussions, and until then, I think I'll sign off. I'll talk to you later. Bye.